Good morning, everyone. So let's get started with where we left off last week. I'll just quickly, once again, rehash what we learned, and then you can ask your questions from that. I know we did rush a little bit. It was quite a bit of understanding of what's 2D NMR. Okay, I'm going to build up on the HMQC. This is the basic pulse program. From here on, I hope everybody gets comfortable whenever I draw pulses and delays of this kind. You had a tau delay on either side, and a 180-degree pulse is applied on the proton channel at the middle of T1 evolution. So basically, this is T1 evolution. I forget the phases that we ended up taking. I guess we took Y phase. Is that right? And both these were X. And of course, this also was kept as X. What did we find as the final density matrix here? Can anybody recollect and help me? It would have been cos of omega s T1 times minus HY. This is what we ended up getting. So therefore, if you keep the receiver phase also along minus Y, you can keep it along plus Y. You just have a minus one there. That's not a problem.
So it would be capital omega C. So it would be capital omega C.
Capital omega C. Okay, thank you. So this was the terminology we used last week. Is that correct? Capital omega C. Thank you very much. So this way, that's the density matrix right before acquisition. And if you keep the receiver phase at minus Y, this will go to plus 1. That's why I did. You can also keep it as at plus Y, just that you'll have minus of this one, which means that all will be multiplied by minus 1. That does not make any huge differences to what we look at. The important observation here is that the density matrix has a cos of omega C T1, meaning that during the acquisition time now, the available parameters that might end up evolving are proton chemical shift, carbon chemical shift, and the scalar coupling between proton and carbon. As I had mentioned, if you are doing decoupling, you will be killing the scalar coupling between proton and carbon. This also you guys got feebly exposed to in the carbon 1D NMR experiment where the proton is decoupled. It's the same idea. Here the proton is acquired while the carbon is decoupled. Okay. So with that being the case, this will go away. And if you see the product operator as HY, you know that the CZ will commute. So therefore, carbon chemical shift will also not evolve. So the only thing that you're left out with is proton chemical shift evolution. And I'm sure from your previous lectures, you would be able to recollect during this acquisition time, you would end up getting a term of I omega H times T2. As a final density matrix, the product of density matrix to the operator minus HY, right? After a time, T2 of evolution. So with that being the case, what you are able to see is that your final signal, if I have to write it, S of T1, T2, S plus of T1, T2, if I have to write it, will be something like cos of omega C T1 times EXP I omega H T2. This is where we left off. And I also requested you guys to change the phase of first 90-degree pulse on carbon. To, I think I said to minus X. And did you guys solve that? What did you get? Whoever solved, can you please tell me what you got? Same at this point of time. So slowly we will realize that if you see the density matrix just before acquisition, we know how to read out how the spectrum should look. Did you get it? Very good. So I'm guessing there would have been a minus sign, but let me see. Omega C T1 HY. This is what you got? Very good. So if you see here, that's exactly how you are able to get the quadrature detection on the proton channel to get a complex oscillation, meaning that e power I omega H T2 came up. Similarly, to get e power I omega C T1, you want the cos part and the sine part. You cannot get it done in one shot. Once again, we will see that in the hardware part, how the direct dimension get the quadrature in one shot. On the other hand, this indirect dimension, what is indirect about it? You don't get the carbon chemical shift directly. You allow for various T1 delays to be changed in your experiments. You acquire multiple one-dimensional NMR experiments by slowly varying the value of T1. Therefore, since you can actually Fourier transform to get chemical shift of omega h, you see the modulation of the proton signal as a function of carbon chemical shift, which will also be an oscillation. Many times when people end up doing Fourier transformation only due to the only the direct dimension, allowing for the indirect dimension to be modulated, one can actually take the trace and actually create an FID for the indirect dimension. Such an FID for the indirect dimension is called an interferogram. FID of indirect dimension is often referred to as interferogram, meaning that you don't have the direct FID, but you can kind of infer the FID by looking at the modulation of the signal. So this way, what you will do is that you will have to do two scans. So let's take a look at how the experiment will be done. For the first value of T1, the phase of the first 90 pulse, we have kept it at Y, and the next scan, it's kept at X. And the receiver phase, you will continue to keep it at minus Y, because you do end up getting minus HY. That will not change. If you end up changing the first pulse, only this part will change. If you're not sure about it, go back and do it. The rest will remain same. Therefore, you have to keep the same receiver phase. You cannot change two simultaneously. You change two simultaneously, the relative phase will only give you cos again. For instance, if you ended up changing from Y to minus X and this minus Y to plus X, then you will once again only get the cos term. You will not get the sine term. So you only have to keep the first pulse as the different phase, while the receiver phase remains constant to get quadrature detection of the indirect dimension. Okay, with this example being done, so what were you able to get? Let me write it. In the first scan, you got cos of omega c T1 times HY, rather minus HY, minus sine of omega c T1 HY. Okay, and from the HY, you will anyway get the complex part, which will be e power I omega h T2. Therefore, you do two scans for every indirect dimension point to get the quadrature of the indirect dimension. Let me do one more step before I allow you to ask questions. Remember, the indirect dimension, the carbon will have a certain spectral width. Let's just take some simple number. Let's assume that we saw an example of 200 ppm of carbon at the spectral width for small organic molecules. Let us say that we are doing a 400 megahertz proton NMR spectrometer. That means carbon is 100 megahertz. 100 megahertz, therefore, indicates the spectral width of carbon in hertz will be 200 times 100, which will be 20 kilohertz. Correct? If it's 20 kilohertz, the dwell time on carbon is going to be 1 over 20,000, which is going to be 10 power minus 4 by 1 by 2, which is going to be 0.5 times 10 power minus 4 seconds, which will therefore translate to 50 microseconds. Just giving an example, if you ended up choosing a certain spectral width for carbon, you have a certain dwell time. So therefore, the next step will be based on this dwell time, where you keep the phases same, while for the quadrature, you end up getting this. So what has happened here, T1 would have been 0. Since T1 would have been 0, you end up getting 1 and you end up getting 0. On the other hand, the moment you have a non-zero dt1, you will actually have a minus cos omega c dt1 times hy minus sine omega c dt1 hy. Since we are receiving on the minus y phase, I'm just going to erase this part, because we know that we will get the proton chemical shift. You have repeatedly done it. So let me only keep the carbon part of it so that you understand. The moment you start to have dt1 that's non-zero, the cosine magnitude will be slightly less than 1. You had 1 because it was cosine of 0. Now you have not cosine of 0, you have slightly greater value than 0. Therefore, it's going to be slightly less than 1. Similarly, previously at a sine value of 0, but now that value is going to be slightly greater than 0. So what you're able to understand and appreciate as you keep on doing for the other increments of 2 dt1, 3 dt1, and so on and so forth, the value for the cos part will keep reducing, the value for the sine part will keep increasing. And remember, since it's a sinusoidal oscillation, it'll go back and forth between -1 and +1. Okay, cos will decrease until 0, it will decrease until -1, and then it'll start to increase from -1 to +1, depending upon the value of T1. And therefore, what you're able to understand, the proton resonance also gets modulated sinusoidally based on the carbon chemical shift. Of course, this value is something that you determine based on the spectral width, and the carbon chemical shift, carbon chemical shift is something that you want to measure, right? And therefore, if you have a readout that changes as a function of a delay that you are allowing to change, you can find one unknown variable. Basically, that will be an oscillation. If you pick up the frequency or the time period of that oscillation, you know what's the offset and therefore the chemical shift of carbon. And the way this has been achieved is by carefully tuning the tau delay to 1/2j. And the 1/2j is specific for 1 bond CH, 2 bond CHS, 3 bond CHS, and so on. As you go more and more in the distance in the bond, the magnitude reduces. The highest of scalar coupling is 1 bond scalar coupling. You're looking at something like 124 hertz to 200 hertz. On the other hand, 2 bond scalar coupling already will reduce to a few tens of hertz. 3 bond will be almost non-existent. It will be less than 10 hertz or something. So what we are able to understand, this way you can still tune for larger J couplings between proton and carbon. But the more important thing that we tend to learn here, only the directly bonded carbon proton will give us signal. 13C bonded proton will only give us signal. If you have a mixture of 12C to 1H and 13C to 1H, this signal will actually be cleaned out by something called phase cycling. We'll come to that later. Okay, because remember, once you excite proton, all protons get excited, irrespective of whether it's bonded to C12 or C13. But the mere fact that you have a carbon-13 pulse and you're nicely tuning the tau delay to only select the coherence that passes through the carbon enables the fact that only directly bonded CH gives you a signal. Did that make sense? So let me pause there, and I hope this has given an idea of how a carbon-proton correlation exploiting the multiple quantum coherence. Why multiple quantum coherence? If you guys go back and take a look and remind yourself, the coherence that's evolving to get the frequency labeling on carbon. What do I mean by that? This part is called frequency labeling. Why is it called frequency labeling? At the end of it, each resonance has a given carbon chemical shift that's labeled based on its frequency. Frequency, it's chemical shift. You can call it chemical shift labeling as well. Okay, the frequency labeling happens with the multiple quantum coherence term, making it a HMQC, heteronuclear multiple quantum coherence spectroscopy. This is how a HMQC spectrum comes up. And the way we move from this signal, what is the signal? So I hope you guys are able to understand, if I take the quadrature in the indirect dimension and I have a quadrature in the direct dimension, my final term will look something like this. The signal will end up looking at as e power I omega c T1, e power I omega h T2. And therefore, if you end up doing a two-dimensional Fourier transformation with respect to T1 and T2, which will translate it themselves to omega 1 and omega 2. Previously, we had only T, and therefore we wrote omega. Now we have T1, we'll write small omega 1, indicating that is the variable Fourier pair of the respective time domain, meaning that T1 determines omega 1, T2 determines omega 2. Therefore, if you end up doing this Fourier transformation, you'll get a convolution of a carbon signal with respect to omega 1 and a proton signal with respect to omega 2.
What is the intensity weighted by?
The question here is, what is the intensity of the signal weighted by? This is an important question because let's go back to the pulse program. You start with the proton polarization. You move the proton polarization to carbon, get the carbon labeling done, and you push it back and detect on proton. First of all, the signal to noise ratio has a very interesting dependence on the excited and detected gamma of the nuclei. If I remember correctly, it will be something like this: excited power 1 and detected power 3/2. So therefore, what are we trying to say? The coil is most sensitive when you excite in proton and detect in proton. One thing. And also, since you're exciting proton and allowing for polarization to get transferred, it's going to depend on proton T1, not carbon T1. True? So therefore, if your T1s are vastly different, anything that has a long proton T1 will have a lower intensity because it wouldn't have recovered as much in the D1 delay, unless you do a short pulsing with steady state scans and carefully tune this flip angle. There are other ways to surmount it. But I'm just giving you some ideas where it would once again be weighted on the proton T1s. Okay. And you're having multiple quantum coherence terms that evolves here, which has very different relaxation characteristics than a single quantum coherence, due to which that will also end up affecting your signal intensity. One important aspect, which I give you as a homework right now, I request all of you to try this. What we ended up doing is to look at how does a directly bonded CH evolve, directly bonded 13C1H evolve in the HMQC. Let's complicate our life a little bit and ask, what will happen when you have something called a passive coupling? What is passive coupling? Previously, you saw the coherence that's generated by a Ca to Ha, directly bonded Ha that's bonded to Ca, both of which are NMR active. You got a correlation. You have organic molecules or even biopolymers which will have these kind of moieties being present. We'll just take a simple instance where the neighboring carbon is carbon 12, so that you don't have to worry about 2-bond HC just for now. But remember, 3-bond proton-proton couplings are also significant. They're not small. Sometimes they're 15-20 hertz. Therefore, what I want you guys to repeat this density matrix formalism on is to add an additional passive scalar coupling term. What is the passive scalar coupling term? This will be pi JHH HAZ HBZ. 2. I forgot a 2. What am I trying to say again? Previously, whatever you evolved in the MQC, we said that it will not evolve with a proton chemical shift. It will not evolve with the scalar coupling, active scalar coupling, which is the one-bonded carbon-proton scalar coupling, because it's multiple quantum coherence. And then we moved on, we only evolved carbon chemical shift here. Now, during this term, if I end up throwing the passive coupling between two protons, remember the 180 pulse will remain for both of the protons, therefore their scalar coupling will evolve. So try to go back and evolve proton-proton coupling for a proton-carbon HMQC. You will understand that the passive coupling will evolve. So what will end up happening finally? Previously, you got a signal based on omega C and omega H. This is the omega 1 dimension. This is the omega 2 dimension in the 2-dimensional NMR spectrum. I'm still drawing the Dirac delta function. If you end up including the passive coupling component into it, this will further get split into a doublet where this will indicate 3JHAHB. Why did I take this long to explain it to you? If there are passive proton-proton couplings, signal will split and will also reduce the intensity of the signal. So there are many factors that affect the intensity of a HMQC signal. One is the proton T1, right? The good thing is that you excite and detect on proton. Slowly, I have started biasing you guys to understand a multidimensional NMR experiment is the most sensitive when you excite proton and when you detect proton. You could have always done other things. You could have excited carbon, detected on proton. You could have excited proton and detected on carbon. There are many things that one could do. But we chose to excite on proton and detect on proton. These are traditionally called the out and back experiment, meaning that the polarization goes out of proton and comes back to proton when you finish. Are one of the most sensitive multidimensional NMR experiments. The intensity depends upon the proton T1 and presence of passive coupling. And whether you like it or not, to decouple the passive coupling is not straightforward because you're applying a hard 180-degree pulse on the proton. If you ended up applying a shaped 180-degree pulse, maybe things will get refocused, but I don't want to go into it because I'm not discussed what shaped pulse. There are always caveats to everything that I say. There are ways to overcome it, but let's talk about the conventional way that people run this experiment. Conventional way people run this experiment is by using a rectangular 90-degree pulse, and a rectangular 180-degree pulse at high power, meaning that these are hard pulses, and therefore they'll excite everything. The passive coupling will also end up playing a role. Any other questions from others?
The graph, the splitting you did on the carbon split horizontally.
Since it's happening in the T1 evolution, you'll see the splitting only in the T1. You'll also have some splitting in the omega 2 also, provided you have the resolution. In theory, you'll get 4. But remember, I'm talking about the evolution of this coupling only in T1 time. And I'm talking about the evolution of the coupling in the T1 time. It will only affect the density matrix in the T1 time, not in the T2.
But the coupling is between the protons.
That's right.
Proton chemical shift.
Proton scalar coupling will evolve in addition to the carbon this thing. Why? Because let's take a look at the term. I see your confusion here, meaning that the term, the MQC term that you have here, MQC term during T1 evolution is 2, what is it, HXCX? Is that what we came up with? And now the Hamiltonian for this passive coupling is pi j HH 2 HAZ and let's say HAX and HBZ. Do you realize these don't commute anymore? Therefore, it will evolve. So proton-proton scalar coupling will evolve when carbon chemical shift is evolving. Therefore, the carbon will be split into proton-proton coupling. Yes, slightly complicated, but yeah.
Difference corresponds to
The proton-proton coupling.
The carbon spectrum.
That's correct. In the carbon dimension, it's a carbon-proton spectrum. Okay. Slightly complicated, but go think about this. Do the density matrix formalism, just invoking it. What you will have is an additional cos of pi j HH T1 times cos of omega C T1 times minus HY. This is what will come up if you ended up doing it. And you have a cos modulation on a EXP omega C T1. Remember, you do quadrature detection to get the EXP term. And therefore, this will split it into 2. Slowly, the idea of understanding Fourier transformation helps. Because cos of theta can be written as e power I theta plus e power minus I theta by 2. Therefore, you will realize that this will go into this and split. And remember, the T1 matches. Well, the HY will go with T2. I agree with the fact that T2 also this proton-proton coupling will evolve. You cannot decouple selectively proton. There is homonuclear decoupling. But when you're doing a regular experiment, you don't do something crazy like that. So it will also evolve. So in theory, you'll get 4 such peaks. But the major problem that comes up is that the acquisition time limits how much you can measure. If you keep the acquisition time on T2 as something like 100 milliseconds, the resolution is 1 over 0.1, which is 10 hertz per point, right? If your 3-bond proton-proton coupling is just at 10 hertz, you will not see that splitting. You don't have the resolution to see it. So in direct dimension, many times you won't see it, but in indirect dimension, small splitting will end up coming. right? Because 10 hertz in a carbon translates on the whatever numbers we have been using. 100 hertz is 1 ppm. So 10 by 100 is 0.1 ppm. This is discernible. You will see a nice doublet that comes up. It won't be resolved until the baseline, but you will see a doublet. I'll try to show it to you. Okay. Complicated matters too quickly. I wanted to say this at the end of the lecture, but I'm happy that you invoked it. Any other questions?
So this is actually regularly used in protein backbone HNH alpha measurements.
That's right.
Coupling measurements via HSQC, right?
Very good example.
You record very high resolution where you give tons of T1 there, and you do see that because you want to distinguish between alpha and beta secondary structures.
Excellent. So what Jeet is trying to add here is a very important point. So what he's trying to make you understand, remember, proton-proton scalar couplings have the Karplus equation running behind, or rather can be empirically defined by the Karplus equation, where if you get the magnitude of scalar coupling, you can get the dihedral angle between two protons. Therefore, he's trying to say, if you end up measuring the HMQC here, you can potentially get the HNH alpha. So generally, this is referred as the HN proton. You can get the 3J HNH alpha coupling when you run the, let's say, nitrogen proton HMQC, or for that matter, even C alpha H alpha HMQC. But the problem with C alpha H alpha is that there are other protons that will be present that will complicate. But on the other hand, for HN, only the H alpha is the 3-bonded coupling. Otherwise, for the C alpha H alpha, you have more. You have HN and H beta being present. So therefore, if you end up acquiring the HMQC for a protein at high resolution, what does he mean by this? Is that the acquisition time on the T1, if you go high enough, right? I just gave you an example of 100 milliseconds. Let's say you go 200 milliseconds, you go to 5 hertz, isn't it? At that point, you'll start resolving. So high resolution just indicates go longer and longer in acquisition time. Of course, you're going to get noise. Therefore, you got to do signal averaging more and more to make up for the noise, to get the signal and get the splitting. And what he's trying to give you an idea is that these scalar couplings would be extremely crucial to define some structural parameters to get the overall structure of the protein. Super point, G. Thanks for adding. I hope I conveyed it to students. Please add more, many things that I might end up missing like this. Slowly, what we are able to see is that we started from the quantum picture, and we are asking how we can exploit that quantum picture to give me an experiment to find a variable to understand molecular structure. Do we see that? Yeah, we are slowly marching towards it. At the end of the course, I hope we are there. Now that the HMQC component is done, we realize that the T1 time, since you have an MQC term, passive couplings evolve. That's a good thing to get some structural parameters, but not all the time you want this to evolve because it reduces sensitivity and resolution, right? So in this aspect, what we are able to see, yeah, the problem stems because of the HX component, right? Somehow if I didn't have the HX component, instead of that, if I had the HZ component, you realize that the 2JHH will not evolve because HZ and HZ will commute. So what do I mean by this? Instead of the MQC, if I have an SQC in the T1 of the form of, let's say, 2HZCX, and that point, the Hamiltonian, let's say HAZ, will be pi JHH 2HAZ HBZ. At this point, these two will commute with each other, and therefore such passive couplings will not evolve. Do you guys agree with me? So therefore, there are some advantages of getting the MQC, but there are definitely more advantages getting the SQC coherence to evolve in the T1 time. An obvious progression for the heteronuclear experiment starting the HMQC is the HSQC, which is the spectrum that I showed you last week on how does a HSQC look for BPTI, ubiquitin, and all the other proteins. A commonly run experiment is the HSQC, not the HMQC. There are advantages for the HMQC, but we'll keep that aside. So let's try to draw a pulse program for HSQC. I request everybody to pay attention here, because once you understand how to do this, it'll be much more easier for you guys to do. Let me pause. Has a question. Yes.
Detected a wide to third of multiple quantum position because FID as even
Yeah, but okay. The question here is that multiple quantum coherence term cannot be detected. How you are detecting it? Is that your question?
the FID is involving in T1 time also.
Sorry?
We do FID in T1 also.
You don't get the direct, you don't keep the receiver on during T1 time. You just evolve T1 several times to get this information. It's indirectly measured. You only measure the proton channel. You do not measure the carbon channel. But as you keep changing the duration, proton signal intensity will be modulated by the carbon chemical shift, which will be an oscillation. And from there you pick it. So it's a multiple quantum coherence that's indirectly detected. What is your question? If I didn't still answer it. Right? So you don't keep the receiver on. For people who are getting confused, do you keep the receiver on during T1? No, we do not. That's why it's indirect detection. You do keep the receiver on here. You do not keep the receiver on here. There are new experiments that do it, but I'm talking about conventional NMR from 80s, 90s, 2000s. People started keeping the receiver on at multiple times in a pulse program in the last 10 years. But I'm keeping that away because we are not talking research, we are talking basics right now. Okay. So, yes.
So what is the number of T1 we are using this experiment?
Good point. So how does that get decided? Okay, let me write the question. Number of points in the indirect dimension. How is it decided? Is that the question? Who was that, Abe or Nikhil?
Nikhil, sir.
Nikhil. So your question is, how does the number of points get determined in the indirect dimension? Is that right? Did I hear it right?
Yes, sir.
So let's go back. We set the carbon spectral width, we set to 200 ppm, which means that the dwell time on carbon was for we are talking about 400 megahertz proton here, and we calculated it to be 50 microseconds, right? That is a dwell time, meaning that the spacing between points while you're acquiring will be 50 microseconds, right? And we know for a fact that the resolution for any FID that you take is indirectly proportional to the acquisition time. So yet again, it says, what is the maximum value of T1 that you're going to reach by adding more and more points to get the necessary resolution? So let us say you wanted to get, let's say you set a T1 max of 50 milliseconds in the indirect dimension. How will you set it? You have 50 microseconds. You have T1 max. So number of points is going to be equal to 50 milliseconds, 10 power minus 3 seconds, divided by the dwell time, which is 50 microseconds. So therefore, the number of points will immediately be 1,000 points to achieve 50 milliseconds. Okay, that means that the resolution will be 1 over 50 or milliseconds. We are talking about now 1,000 over 50, which will be 20 hertz per point. So depending upon what is the resolution you want to obtain, you will acquire that many number of points. Slowly, what you are able to catch up is that the spectral width that you kept that resulted in a short dwell time is going to cost you more and more points. So common thing that people do is to keep as short a spectral width in the indirect dimension so as to achieve a certain resolution. So this is exactly why I gave the lecture of how do the number of points, acquisition time, all that get related to one another. Okay, so similar to the aspect that for the direct dimension, which is T2, you have a spectral width. Rather, I cannot write spectral is in time dimension. You have a dwell time, right? 12 time in spectral width are inversely related. So it will go to 1 over spectral width on proton in hertz. Remember, be careful, the units matter. Correct? And this is the dwell time. You have a total acquisition time that's determined by T2. And therefore, the number of points in the proton dimension get decided. Everybody followed? Everybody agrees? Yes? Similarly, in the T1 dimension, the DT1 is set by the spectral width of the carbon in hertz. And based on approximate T2s or the resolution you want, for the example that I took, it comes as 20 hertz by point. It's not great. You're talking about 10 hertz couplings. You will not measure 10 hertz coupling when your resolution is 20 hertz. You need to at least be 10 or lower. Even 10 won't make the cut. You should be around 5 to measure it properly, reliably. If you're at 2, then you'll get it. That's what Jeet was mentioning as high resolution HMQC. As this number goes lower and lower, 10 hertz is a higher resolution than 20 hertz, and 5 hertz is a higher resolution per point than 10 hertz. Okay, and that gets decided by the acquisition time. So basically, so let me erase this and call it T2 max, which is acquisition time. Similarly, you will have a T1 max, that's the indirect dimension acquisition time. That will determine the number of points in the 13C dimension. Thank you for raising this point. What we are seeing here, we first did a 1 scan 1D experiment. Let's assume that the concentration is high enough that single scan is enough to get your signal, more than 3:1. Okay. You did a single scan experiment. Let's say it took 1 second for you to do it. Then what did you say? I wanted to do 2D, right? The moment you go to 2D, you have to have an interscan delay so as to make sure you can repeat. That adds a lot of time in order to measure that experiment. Even for a single scan, you have to have the recycle delay. But remember, a single scan will not give you the indirect dimension frequency. You need a quadrature and a bunch of points that are going to be there. So if your 1D took a single scan, how long will a 2D take for this example? It will be 1 times 2, because 2 due to the quadrature on carbon, and 1000 points on the indirect dimension. So how many number of 1Ds you got to acquire? You got to acquire 2000 1D NMR experiments to get a 2D. As much as we said, the 2D NMR is super helpful in getting resolution to pick as many different peaks which are overlapped. It comes at a cost of total measurement time. If the 1D took 1 second, this is going to take approximately 2000 seconds. That's because of the indirect dimension points. I hope I have hit 2 birds in a single stone, saying how do you determine the number of points in the indirect dimension, and therefore why does a 2D NMR experiment take a long time? Many times the 2D NMR experiments are not very sensitive, so therefore a single scan will also not work. You will end up doing multiple scans, 8 scans, 16 scans, sometimes 128 scans. Slowly you realize 2000 seconds, how much is that? About 30 minutes. Is that right? Divided by 60. Yeah, it's about 30 minutes. Is that right? Right. So therefore, 1 second became 30 minutes. And if you have to increase it by another 8, let's say 8 scans have to be acquired, it immediately goes to 4 hours. If you have to run something like 128 scans, goes to overnight. All that depends upon the concentration, labeling, and everything that you're working with. Yeah. So that's why 2D NMR, although super helpful, comes at a cost. Everything that you get, you gain, comes at a cost of something else. It's always a compromise. Good question, Nikhil. I hope I've been able to answer your question in this regard. So let's take an example. I'm going to ask you guys for this HMQC, what will be the parameters? Let's say you're measuring between 0 to 10 ppm on a proton. And then you're measuring between, say, 80 ppm and 100 ppm on carbon, just for an example. On a 400 megahertz NMR instrument, the questions are thus: what is the carrier position in ppm for proton and carbon? This is the first question. what is the spectral width in ppm and hertz for both the dimensions? What is the dwell time for both dimensions? And if my T2 max is 100 milliseconds and T1 max is 32 milliseconds, what are the total number of points in either of this dimension? Okay, can you guys calculate it and come for next class? This will help you understand how to actually set up an NMR experiment. Make sense? Any other questions before we go to the HSQC? I'm okay going a little slower, but I want everybody to catch up to the idea of what we are trying to understand and how are we getting the information that we seek.
What is the order of like how much is T1 and T2 for proton?
So your question is, how much is T1 for proton and T2 for proton? All right. I want to say something like this. Jitu, that be a reasonable number? His question is, what will be the T1 and T2 of proton for something like reasonably sized molecule?
So then, can you go back to the previous page? We have the like 50 milliseconds as the but the spin won't recover. So how do you do the experiment again for the next point?
That is always a D1. So the question is, how will we repeat the experiment? We are not writing the D1 explicitly, but there is always a recycle delay here, which I explained to you last week or a week before.
And that's why we let the spin recover.
That's right. You have to leave that time for the spin to recover. And that takes time.
The 50 milliseconds, 50 microseconds is the acquisition time.
The 50 milliseconds is the maximum T1 you're going to. So for instance, you're changing DT1, right? Next point will be 2 DT1. Until how long will you go is the question. That's what was Nikhil's question. Okay, you can stop with 2 points. You can stop with 4 points. You can stop with 10 points. Where do you stop is this question. You can add, if you want a higher and higher resolution, you want more and more points. But the problem of getting more and more points, as you are rightly able to understand, if this becomes 50 milliseconds, if your 1 over 2j is about 4 milliseconds, 4 plus 50 plus 4 is already 58 milliseconds. But signal dies within 100 milliseconds, you have only 40 milliseconds of signal here. Yeah, that's the problem. As you start to increase these times, depending upon the T1, T2, for very large size molecules, T1 increases, T2 decreases. It kind of kills us both ways. T1 increases, meaning that the recycle delay has to be long. T2 decreases, meaning that as it passes through and gets back, the death is faster and more. And therefore, you will not be able to get a high resolution spectrum for larger molecules. That's an impediment for large molecules running multi-dimensional NMR experiments. Therefore, if you have more and more pulses, more and more transfers, it's just going to be less and less sensitive. It does give you the exquisite information, but the sensitivity does take a hit. And therefore, the total measurement time gets implicated. Okay. Let me repeat again. I'll be happy going slower so that you guys get these aspects. Okay. Any questions from Pune? Feel free to ask. Okay, let me move on. Last 10 minutes available. As much as we are doing very important stuff in the last 10 minutes of every class, today's class is also going to be like it. Take a look at this pulse program called HSQC and come tomorrow. We'll revise again like the way I did today. Today morning, I repeated HMQC. Tomorrow morning, I'll repeat HSQC. But let's get something started so that you guys start thinking. We just said that the NQC is a problem because of passive coupling. So I'd prefer a SQC over NQC if I can. So we'll quickly see how a MQC experiment can be built. This is a module that you guys have seen over and over again. What is this module called? Yes, this is the inept module. where the tau delay is set to 1 over? Excellent. 1 over 4j, right? So you see that at this juncture, you have created something like single quantum coherence term. So if you understood HMQC, HSQC is going to be a cakewalk. The moment you have it, you guys might remember the Hamiltonian once again goes back to omega h hc, omega c cz, pi j hc, 2 hz cz. Is that right? What we need is only the carbon chemical shift. We do not want proton chemical shift or the proton carbon scalar coupling because we want to decouple the proton from carbon, right? And the HMQC, this 180 pulse achieved many things. One of the things it achieved was to decouple. Although you created an MQC term, then you might always argue, take this 180 off. If you take the 180 off, proton chemical shift will evolve during the entire stuff. So you have to have the 180 there. So indirectly, the 180 also did decoupling, but it's all even not required for an MQC. But here, we will exploit the same idea where we will end up having a 180 at the middle of T1, where the evolution still happens here. And this 180 is applied right in middle of T1 evolution. What are we doing here? Only if you applied simultaneous 180s on both the channels, scalar coupling would evolve. This we learned when we learned the spin echo. If you end up applying the 180 on only one channel and not on the other channel, scalar coupling will not evolve. So very simply, what we have done is to kill the proton chemical shift will anyway not evolve because it commutes, and kill the scalar coupling evolution between proton and carbon. Therefore, the only term that will evolve during this period is the carbon chemical shift. So what's going to end up happening at this point of time? You will have something like Hz Cy cos omega c T1 minus 2 Hz Cx sin omega c T1. Right? Then the next series of steps are going to be very easy. Similar to the aspect how you converted Hz to HzCy, you want to convert back HzCy to Hx or Hy. Okay? How would we do it? First of all, we need to apply a 90-degree pulse. The moment you apply a 90-degree pulse to this, and let me run with only one of the terms, maybe I'll run with the cos term. What is going to happen? 90-degree pulse simultaneously, Hz will become minus Hy, and X phase pulse Cy will become Cz, cos omega c T1. All I did was apply the 90-degree pulse simultaneously. Then let's say you have once again the inept delay. This is called the reverse inept, not refocused inept. This is called reverse inept. Why reverse? Inept is one where that pushes proton to carbon. Now you're at carbon, you want to push it back to proton. So it's reversing the inept. If you did not have this portion, this will, and the 90-degree pulse, it will be called a refocused inept. So be careful. If you did not have this, like from here to here, if you did not have, that'll be refocused inept. But we are talking about the reverse inept in this case. So what is reverse inept going to do? Since you have a tau that is set to 1 over 4j here as well, the terms that are going to be present are, will proton chemical shift evolve? Why? Why it does not evolve? Very good. You have a tau 180 tau, proton chemical shift will not evolve. Will the carbon chemical shift evolve? No, once again, not because of the tau 180 tau, because Cz will commute with Cz, therefore it will not evolve. Will the scalar coupling evolve?
Yes.
Yes, because the 180 is applied simultaneously. Therefore, in this tau 180 tau period, only scalar coupling will evolve, which will result in the following. So let me write it in the next page. Minus 2 Hy Cz cos omega c T1 with a tau 180 tau will result in 2 HYCZ cos pi j tau, pi j HC tau, cos omega C T1 minus 2, minus HX sine pi j HC tau cos omega C T1. The cos omega C T1 will remain. All I am doing is evolving this component with respect to scalar coupling. If you set tau appropriately to 1/4j, you will end up getting the density matrix at that point as minus hx times cos omega C T1. Can always now set the acquisition along the minus x phase in this case and decouple. You will yet again get a carbon proton correlation. All the other concepts that I spoke about, T1 evolution, DT1, holds good for this experiment also. If you end up getting the quadrature, here the quadrature is done by changing the phase of this pulse from an X to a Y phase, for instance. Okay, so let me add that here. So if this pulse is changed from X to Y, you'll get the quadrature. You have to still keep the receiver along minus X. I hope now people are able to understand how I choose the receiver. If it's a minus HX term, I'll keep the receiver along minus X. Right? If you end up changing the first pulse, first 90-degree carbon pulse, change from X to Y, you will get the sine term. So this will be the repeated way a 2D is done. You'll get the cosine modulation of the carbon chemical shift from the proton FID. Repeat the experiment by doing a quadrature along the indirect dimension. Acquire all the points across the dwell time and through the acquisition time. Do a two-dimensional Fourier transformation. You'll get the HSQC. All the other narratives literally remain same between HMQC and HSQC. The major difference that you have been able to achieve here is that since you have created a single quantum term, which is HZCY, this will not evolve with any other passive proton-proton coupling that will be present. So therefore, we'll have one more exercise for tomorrow. Kindly remind me these exercises for tomorrow so that we will understand things better. Please definitely do the X comma Y to make sure you understand cos and sine component comes up. In addition, I want you to repeat the density matrix formalism without this 180-degree pulse. Just this pulse being deleted. We'll see what comes up. So that will be the end of the class. Any questions, quick questions, doubts? Excellent. So that requires a lot of chewing for you guys. Go chew it today. Think about it and come back. But I promise you, the moment you think and understand it, you don't have to repeat it again. We are repeatedly exploiting the same concepts and over and over and over and over again. Okay. Thank you very much.